Welcome to Section 5, Lesson 10. In the previous lessons we built the function concept and the standard function families. Today we add two specific symmetry classifications that some functions satisfy even functions and odd functions. The classifications are determined by simple algebraic tests on the function rule, and they have clear graphical signatures that make even-odd identification fast and visual. Most functions are neither even nor odd, so the two categories are special properties rather than universal ones, but when a function does satisfy one of the symmetries, the property simplifies many later calculations significantly. Today we lock in the definitions, the algebraic tests, and the graphical signatures. First idea on the board, a function f is called even if f of negative x equals f of x for every x in the domain. Geometrically, this condition means the graph of f has y-axis symmetry. The value of the function at any positive input is the same as at the corresponding negative input. Examples include f of x equals x squared, f of x equals absolute value of x, and any function whose rule contains only even powers of x and constants. Even functions have v-shape, u-shape, or other left-right mirror symmetric graphs. A function f is called odd if f of negative x equals negative f of x for every x in the domain. Geometrically, this condition means the graph of f has rotational symmetry of 180 degrees around the origin. Rotating the graph by half a turn around 0,0 gives back the same graph. Examples include f of x was x, f of x equals x cubed, and any function whose rule contains only odd powers of x with no constant term. Odd functions have S-shape line through origin shape or other origin rotational symmetric graph. Third idea, most functions are neither even nor odd. Adding any non-zero constant to an odd function destroys the odd property. Adding an odd power term to an even function destroys the even property. The function f of x equals x plus 1 is neither, because it has both an odd term x and a constant term 1, breaking both symmetries. Always test the symmetry algebraically before claiming a function is even or odd. Compute f of negative x and compare to f of x and to negative f of x. If neither comparison gives equality for every x, the function is neither even nor odd, which is the most common case. A function f is even if f negative x equals f of x for every x. Geometrically, the graph of an even function has y-axis symmetry. Reflecting the graph across the y-axis gives back the same graph. Polynomials with only even power terms and an optional constant are even. Examples include x squared, x to the fourth, x squared plus 1, and absolute value of x. A function f is odd if f of negative x equals negative f of x for every x. Geometrically, the graph of an odd function has 180 degrees rotational symmetry around the origin. Rotating the graph half a turn gives back the same graph. Polynomials with only odd power terms and no constant are odd. Examples include x cubed plus x to the fifth. Step 1 in the algebraic test. Compute f of negative x by replacing every x in the rule with negative x. Carefully apply the substitution including the parentheses to protect signs and exponents. The result is an expression in x that you compare to f of x and to negative f of x. Step 2. Compare. If f of negative x equals f of x as algebraic expressions, the function is even. If f of negative x equals negative f of x as algebraic expressions, the function is odd. If neither equality holds for all x, the function is neither even nor odd. Both checks must work for every x to qualify, not just for one or two specific values. Step 3. The graphical interpretation provides a fast visual check. Even function graphs are mirror symmetric across the y-axis. If you fold the graph along the y-axis, the two halves match. Odd function graphs are rotationally symmetric around the origin. If you spin the graph half a turn around 0,0, you get the same graph back. Both visual tests are quick and reliable, complementing the algebraic test. Here is the first worked example. Classify the following functions as even, odd, or neither. F of x equals x squared, g of x equals x cubed, h of x equals x cubed plus x, k of x equals absolute value of x, and mem of x equals x plus 1. Test f of x equals x squared. Compute f of negative x. Substitute negative x and get the quantity negative x squared, which equals x squared. So f of negative x equals f of x. The function is even. Graphically, the parabola y equals x squared is symmetric across the y-axis as expected. Step 2. Test g of x equals x cubed. Compute g of negative xc, substitute, and get the quantity negative x cubed, which equals negative x cubed. Compare to g of x equals x cubed and to negative g of x equals negative x cubed. We get g of negative x equals negative g of x. The function is ODD. Graphically, the cubic yy equals x cubed has the S shape with rotational symmetry around the origin. Test h of x equals x cubed plus x. Compute h of negative x, the quantity negative x cubed plus negative x equals negative x cubed minus x equals negative the quantity x cubed plus x equals negative h of x. So h of negative x equals negative h of x. The function is ODD. Both terms x cubed and x are odd power terms, and the sum of two odd functions is odd. Test k of x equals absolute value of x. Compute k of negative x. Say absolute value of negative x equals absolute value of x because absolute value strip signs. So k of negative x equals k of x. The function is EVM. Graphically, the V shape of absolute value is symmetric across the y-axis as expected. Test m of x equals x plus 1. Compute m of negative x plus 1. Compare to m of x equals x plus 1. Not equal x plus 1 versus negative x plus 1 are different unless x equals 0. Not even. Compare to negative m of x equals negative x minus 1. Not equal negative x plus 1 versus negative x minus 1 are different. Not odd either. So m of x equals x plus 1 is neither even nor odd. The constant term plus 1 breaks both symmetries. So the classifications are f even, g odd, h odd, k even, m neither. The big lesson from this example is the algebraic test workflow applied to several different function shapes. Even functions contain only even powers and constants. Odd functions contain only odd powers and no constant. Functions with mixed odd and even content or non-zero constant terms are usually neither. Memorizing the polynomial structure shortcut speeds up the classification on common functions, while the algebraic test handles the harder cases reliably. Here is the second worked example. Classify the function f of x equals x squared minus 4 divided by the quantity x cubed and use the result to predict the symmetry of its graph. Step 1. Compute f of negative x by substituting negative x for x in every position. The numerator becomes the quantity negative x squared minus 4, which equals x squared minus 4 because the squared term is the same. The denominator becomes the quantity negative x cubed, which equals negative x cubed because the cube power is odd. So f of negative x equals x squared minus 4 divided by negative x cubed. Step 2. Simplify the fraction. Factoring the negative out of the denominator, f of negative x equals negative the quantity x squared minus 4 divided by x cubed. The original f of x is x squared minus 4 over x cubed, so we have f of negative x equals negative f of x. Step 3. Conclude. The condition f of negative x equals negative f of x is the odd function condition. So f of x equals x squared minus 4 over x cubed is an ODD function over its natural domain, which excludes x equals 0 where the denominator vanishes. Step 4. Predict the graphical symmetry. Odd functions have 180-degree rotational symmetry around the origin. So the graph of f passes through the origin in spirit, even though x equals 0 is excluded from the domain, and rotating the graph half a turn around the origin gives back the same graph. The graph has the characteristic odd function look with branches going opposite directions on opposite sides of the y-axis. Step 5. Verify with a specific input pair. F of 2 equals 4 minus 4 over 8, which equals 0. F of negative 2 equals 4 minus 4 over negative 8 equals 0. Both are 0, consistent with f being odd because 0 equals negative 0. Try x equals 1, f of 1 equals 1 minus 4 over 1 equals negative 3. F of negative 1 equals 1 minus 4 over negative 1 equals 3 equals negative f of 1. Match. So f is odd with origin rotational symmetry. The big lesson from this example is the algebraic test applied to a more complex rational function. The numerator's even power structure and the denominator's odd power structure combine to produce the overall odd classification. Working through the substitution step by step, including the sign tracking on each power, is the key craft skill. Practice the test on a few more examples, and the workflow becomes automatic for any function expression. 3 mistakes that catch every algebra student during their first weeks of even-odd classification. Each one is fixable with a small explicit habit applied on every problem. First mistake: concluding even or odd based on testing the algebraic property at only one or two specific input values. A student finds that f of negative 1 equals f of 1 for some function and concludes the function is even though the test passes only by coincidence at that specific input pair. The fix is to require the test to work as an algebraic identity for all x by manipulating the algebraic expression for f of negative x and comparing to the algebraic expressions for f of x and negative f of x. The for all x condition is essential and cannot be replaced by a single example. Second mistake: forcing the classification into even or odd when the function is actually neither. A student looking at f of x equals x plus 1 tries hard to make it fit one of the two categories, eventually misreading the algebra to claim it is odd. The correct classification is neither, because the constant term breaks both symmetries. The fix is to accept that most functions are neither even nor odd, and to check both algebraic conditions explicitly. If neither comparison gives equality, the function is neither, full stop. Third mistake: sign error when computing f of negative x for odd power terms. A student looking at the term x cubed substitutes negative x and writes the result as x cubed instead of negative x cubed, missing that odd powers carry the sign through. The rule is that the quantity negative x raised to an odd power equals negative the quantity x raised to that power, while the quantity negative x raised to an even power equals positive the quantity x raised to that power. The fix is to write each substitution explicitly with the parentheses and apply the power carefully, especially for odd powers. Even and odd function classifications are foundational symmetry concepts across physics, signal processing, calculus, and computing. Anywhere the underlying problem has a left-right symmetry, the even-odd classification of the relevant functions exploits the symmetry to simplify analysis. 4 broad sectors below. In physics, the symmetry of a potential energy function determines the symmetry of the wave functions in quantum mechanics. Even potentials like the harmonic oscillator produce wave functions that are alternately even and odd by quantum number. Odd potentials produce only anti-symmetric solutions. Symmetry classifications are central to all of quantum theory and to many other physics fields, and the even-odd algebra you learn today is the literal foundation of those classifications. In signal processing, every signal can be uniquely decomposed into an even part and an odd part. Signal of t equals even part plus odd part, where the even part equals 1/2 times signal of t plus signal of negative t, and the odd part equals 1/2 times signal of t minus signal of negative t. The decomposition simplifies Fourier analysis, where even functions have only cosine components in their spectra, and odd functions have only sine components. The decomposition is a foundational technique across audio engineering, image processing, and communications. In calculus, the integral of an odd function over a symmetric interval like negative a to positive a equals 0 exactly, because the contributions from the left half and the right half cancel by symmetry. The integral of an even function over the same symmetric interval equals twice the integral over 0 to a, because the two halves are identical. These symmetry shortcuts can save enormous amounts of computation when applicable, and recognizing the even-odd classification before integrating is a key calculus craft skill. In computer programming and numerical analysis, even-odd classifications enable computational optimizations. If a function is known to be even, you only need to compute it for non-negative x and reflect to handle negative x. The same trick halves the work for tabulated functions, lookup tables, and many simulations. Recognizing and exploiting symmetries in code is an efficiency technique that scales the same way the mathematical analysis does. 3 things to take with you from this lesson today. Even and odd function classifications are foundational symmetry concepts across physics, signal processing, calculus, and computing, and recognizing them on a function lets you exploit the symmetry to simplify many later calculations. First, a function is even if f of negative x equals fx for every x in the domain. Geometrically, the graph has y-axis symmetry reflecting across the y-axis gives back the same graph. Examples include f of x equals x squared, f of x equals absolute value of x, and polynomials with only even power terms and constants. Even functions are common in physics potentials, in cosine functions, and in many other applications where a left-right mirror symmetry holds. Second, a function is odd if f of negative x equals negative f of x for every x in the domain. Geometrically, the graph has rotational symmetry around the origin. Rotating by 180 degrees gives back the same graph. Examples include f of x equals x, f of x equals x cubed, and polynomials with only odd power terms and no constant. Odd functions are common in sign displacements, in sine functions, and in many other applications where a flip and negate symmetry holds. Third, most functions are neither even nor odd. Adding any non-zero constant to an odd function destroys the odd property. Mixing odd and even terms produces a function that is neither. Always test both the even condition and the odd condition algebraically. If neither holds for all x, the function is neither, which is the most common case. The classification must work as an algebraic identity for all inputs, not just for one or two specific values. Coming up next, the lesson called Combining Functions, where we revisit the standard arithmetic operations addition, subtraction, multiplication, and division applied to two functions to produce new functions. Function arithmetic complements function composition from earlier in the section and gives a complete toolkit for building complex functions from simpler ones.